Moving past hydrogen, we get to obviously molecules and atoms with more electrons and more orbitals than just the 1s orbital to deal with. So we're going to take this step by step. We'll start with lithium, and what we're going to do is look at diatomic molecules. Now there are some kind of guiding questions for coming up with orbitals and molecular orbitals from atomic orbitals and how to put the electrons into these. So these are listed in your book on page 376. Basically, number one is that the number of molecular orbitals formed equals the number of atomic orbitals that you start with, that you're combining. The atomic orbitals combine most effectively with other atomic orbitals of similar energy. So when we do the diagrams, you see that the energy level of the atomic orbitals should be similar, and we're working with monatomic, diatomic, mononuclear. So same element as both of the elements that are bonded together, both the atoms that are bonded together. But you can have different elements bonding together, and we'll look at examples of that. Number three, the effectiveness to which the atomic orbitals combine is proportional to their overlap. So the better overlap that we get, so again, that idea of the valence bond theory, the better the overlap we get, the lower the energy of the bonding molecular orbitals, so the more stable they become. And then we have to have an equivalent raising of the anti-bonding molecular orbitals. Number 4 and 5 are both similar to the rules that we used for filling up atomic orbitals, in that molecular orbitals can also only accommodate 2 electrons with their spins paired, so in opposite directions. And if we are filling up molecular orbitals that are at the same energy or degenerate, one electron is going to enter each of those orbitals first with the same spin before pairing occurs. Again, that's known as Hund's rule. So if we go back to this and we look at the lithium, so Li2, remember that this is a picture we have in our mind with the bonding sigma orbital, looking at that oval with more electron density between the nuclei, and the anti-bonding 1s orbital with the electron density located outside the internuclear distance. And just a reminder, we've got that node coming down here where there's no electron density. This is where we added the wave functions together, and there was a net canceling out of those wave functions. So we have no electron density between them in the anti-bonding. Again, it's part of the reason why it's anti-bonding. We do more electron density outside the internuclear distance, which would tend to pull the nuclei apart. So if we look at this in a more practical standpoint, now lithium is going to have both a 1s orbital as well as a 2s orbital. So and again, if we're combining 2 lithiums together, the energy level of these would be the same. So if we think of energy over here on this axis, and the 2s orbital would likewise be that energy level there. We have the bonding, so sigma 1s, the sigma star 1s. We would have the sigma, now 2s, and sigma star 2s. So here would be all the orbitals we had to fill, and then we put the electrons in for both of our lithium atoms. Filling these electrons into the orbitals, then, we would have, fill lowest energy level first, and we'd have this situation here. Our bond order, remember that was one of our questions we would want to ask. Our bond order, obviously the ones in the 1s, the sigma 1s and the sigma star 1s are going to cancel each other out. So if we just look at the 2s, we end up with 2 electrons that are involved in bonding. No electrons are involved in anti-bonding. And if we divide that by 2, we get a bond order of 1. So we would expect the lithium, the diatomic lithium, to behave as if it had a single bond, or a bond order of 1. Now, if we wanted to go to the next element, so Be2, so let me erase the lithium here. Go with Be2. Now, beryllium is going to have 2s2, so there's 2 more electrons there, so obviously we would populate that next, the sigma star 2s. So now instead of having 0 antibonding electrons, we would have 2 antibonding electrons. So for the Be2, we would end up with a bond order of 0. So we wouldn't expect that beryllium to form a bond with itself, to form the diatomic. All right, now we're ready to move on to larger ones. Before we do that, we're going to go back through and do the linear combination of our p orbitals, which is going to be a little bit more complicated. First of all, if we define the z-axis as the internuclear axis, so we're going to make z as the internuclear axis. We're going to have y running vertically, and then we'll make x the axis that's running out of the board, for starters. Now, I'll try and draw this, and then we'll show you pictures of them. So the PZ orbitals, if I take 2 of them and I look at the overlap here, and again, I'm going to look at the combination where we have a phase that looks like this. So here would be the sigma y, or the y, the wave function for the pz on this one, the wave function for the pz on this one. And again, you notice that in this combination, the area between is out of phase. So what we'd end up with then, we do our 2 nuclei here. Linear combination would end up with a node running down through the middle, and we would have a small lobe here, and if we made the size of the lobe that's between the nuclei smaller, the size outside is going to have to be larger. Size inside is smaller, outside is larger. Now, we might ask is the shading on this. Remember, the shading represents the phase, the positive or negative. Let's go back for a moment just to take a look at our orbitals here. If we think about the orbitals, that node that runs down through the center of the nucleus on a p orbital, what happens there is, remember, the node occurs where the wave function crosses over the axis, the x-axis. And so when it does that, it changes sign. And so that's what the phases are here. So whenever you go across the node, you're going to change from one phase to the next. Okay, it's not going to be significantly important to us, but it does help explain why we would get that node when we did a linear combination of these 2. The other combination we get looks something like this. All right. And then here, notice that we have constructive interference in the bonding region here. Right. So what we're going to end up with then is a net increase in electron density between the nuclei. So we'll bulge that part out. And then outside the internuclear distance, we would expect the electron density to get slightly smaller. And the way I've drawn it here, those would be the shaded regions or different phase there. Right. So this would be our sigma 2p. It's a direct overlap right between the nuclei, so it's a sigma. And up here we would have our sigma star antibonding 2p orbitals. Right. So that's the direct overlap. So there's the sigma bond that can form from two pz orbitals that are directly overlapping. Next, let's take a look at what happens if we combine two py orbitals. So our possible combination, so y is oriented in the vertical direction. So we're going to draw one orbital like this. And then here's the potential overlap. And again, I'm going to show where the phases look like this for this part. And where the overlap is there and here, we get destructive interference. So what we'd end up with then is a little bit more electron density out away from the internuclear distance. Okay, so something similar to this. And if we do the other combination, so this time they're in phase, now we get a picture something like this. And with the familiar shape of, you guessed it, a pi bond. So here we would have a bonding pi 2p, and up here we would have the anti-bonding 2p. So again, these occur from the overlap or the linear combinations of the py atomic orbitals, creating both the anti-bonding at the top and the bonding type orbitals. If you did the px, it would be exactly the same as this, only the orbitals would be oriented directly coming out of the plane of the board, but you would get the same type of overlap and that same pi bonding and pi anti-bonding orbitals. So to get a better, more professional looking picture of this, we have the one up here. So up at the top we have our two pz orbitals overlapping, creating our bonding and anti-bonding orbitals. And then in the lower part, we get the two pi overlaps that are occurring, or the sideways overlaps, I guess they call it, of the 2px and the 2py. Now, for an energy level diagram of this, to kind of summarize all this stuff into relative energies, we would get something like this. So for the second level, we have our combination of our atomic orbitals, our 2s atomic orbitals, into sigma 2s and sigma star 2s. And then if we combine do linear combinations of the two p's, we have that sigma 2pz, right, direct overlap. And then we have the two pi, or sideways overlaps, of the 2px and the 2py. And then, of course, above those, we get the anti-bonding pi star 2p and the sigma star 2p. So what we're going to do in class, then, is work on continuing across the second period with B2, C2, N2, O2, F2, and Ne2, and look at those different combinations. And then we'll look at some heteronuclear combinations, too, where we change the atoms that are bonded together.